Let me introduce our next speaker, Mariia Serdiuk.
Thank you. So my topic is fundamental solution of non-Archimedean pseudo-differential equation of p-adic argument. It was done in collaboration with Alexandra Antoniuk and Anatoly Kochumey. Pseudo-differential equations for complex valued functions defined on non-Archimedean local fields, in particular the field of p-adic numbers, which we will focus on, are becoming increasingly important, both in view of rich mathematical structures involved in their studies and due to emerging applications. The basic linear operator defined on complex or real-valued functions on a non-Archimedean local field is the fractional differential operator d alpha. This operator was studied by Vladimirov, and it was shown that its properties are much more complicated than the properties of a classical derivative. If you consider a simple evolution equation with the operator d alpha in the p-adic time variable t, then such equation does not have a fundamental solution. Moreover, if we consider the point spectrum of this operator, it will have infinite multiplicity, which does not correspond to the classical case. However, it was found by Anatoly Kochumey that some of the evolution equations of this kind behave reasonably, which is to say they act similarly to classical differential equations if one considers only solutions that depend on modulo of t. These solutions are called radial solutions. This observation has led to the concept of non-Archimedean wave equation possessing various properties resembling those of classical hyperbolic equations up to the Huygens principle. So first we need to define the p-adic space. So we start from the field of rational numbers Q, and we introduce a norm on this field by the following rule. The norm of 0 is equal to 0, the norm of x is equal to p to the power minus gamma of x, where p is a prime number and gamma of x is defined from the following decomposition. Here p does not divide the integers m and n. This norm is called the p-adic norm. It satisfies all the norm axioms, and the third axiom, that is a triangle inequality in a more strong form. So norm of x plus y is less or equal than maximum of norms x and y. Hence, this norm is called non-Archimedean. The completion of the field Q with respect to this norm is called the field QP of p-adic numbers. We will need to denote this subset of QP with plus, which means the t for which modulo of t is less or equal than 1. The function phi, defined on QP with values in complex numbers, is said to be locally constant if there exists such an integer L that for any x, the following condition holds. The smallest of such numbers L is called the exponent of local constancy of the function phi. We denote by d of QP the linear topological space of all locally constant functions phi with compact supports. The strong conjugate space d prime of QP is called the space of Brouwer-Schwarz distributions. We can define the Fourier transform on QP in the following way. So first we define the additive character of QP in this way. And the Fourier transform of a test function phi is defined as the following integral. Here this character plays a role of what the exponent is in the classical case. Then we have the inversion formula, and we can also define the Fourier transform for a distribution in space of distributions. We will work with Lizorkin spaces. So we define two subspaces of locally constant functions with compact supports. So the first one is psi. It is defined by functions that are equal to 0 and 0, and the space phi is equal to all functions that the integral is equal to 0. This space is called the Lizorkin space of test functions of the second kind, and the conjugate space is called the Lizorkin space of distributions. The most important property of the spaces is that the Fourier transform is a linear isomorphism from psi onto phi, and from phi prime onto psi prime. And at the same time, you can consider the Fourier transform as a linear isomorphism from phi to psi. We will define pseudo-differential operators. So it is an operator defined on some open set of the following form. So here we have the additive character IP, and this function A of psi x is called the symbol of this operator. And this psi tilde is a Fourier transform which we defined before. So the most basic case of the pseudo-differential operator is the operator d alpha. It is defined by a following formula, and it can be defined on all locally constant functions with compact supports, and it acts on the space L2. On the other hand, if we consider the Sorkin space phi, it transforms phi onto phi, and the same for space of distributions. We can also define this operator in n-dimensional space. So we just define the norm of x as maximum of norms of coordinates, and the operator is defined in the similar way. The operator d alpha can also be represented as a hypersingular integral operator. So for any phi, we have the following formula. And in contrast to the previous formula in terms of the Fourier transform, this expression actually makes sense for a larger class of functions. In particular, it is defined on constant functions and is equal to 0 on constants. Similarly, for n-dimensional space, we have this formula for the operator d alpha. So in previous works, the equations for functions of one variable were considered. So this equation 5 was studied by Cauchy, and here the Cauchy problem is considered for the following equation. And it was proved that this nonlinear integral equation, which corresponds to this differential equation, is locally solvable, and we can extend its solution to the whole field QP, and then the solution satisfies the Cauchy problem. In my previous work, I considered the equation similar to 5, but with weak degeneration, which means that we have this multiplication by module t to the power gamma, and the similar properties of this equation were proved in the case when gamma is less than minimum of 1 and alpha. So next step was considering equations with regular singularities, which means that this parameter gamma that we had here is equal to alpha and not less than alpha. So in this case, we study the equation for which the right-hand side is linear and can be decomposed into power series. So we suppose that the coefficients an satisfies the condition 9, and that the function u can also be decomposed into series of the following form, where un are some complex coefficients. We can formally substitute this series into our equation, and in the case when alpha is not equal to beta n, we obtain the following system. And we will call the solution of this system the formal solution of our equation. So the main result was this theorem. If in the decomposition of the right-hand side a0 is either equal to 0 or a0 is equal to this expression, here gamma p is the p-adic analog of the gamma function. So if this condition holds, then the formal series is a formal solution to the equation, and it is locally absolutely convergent. And we also can find the coefficients from the following relations. If this condition doesn't hold, so if A0 has any other form, then the equation only has a zero solution. Next, we consider the problem of finding radial eigenfunctions of the alpha. So we suppose that alpha is less than 1 and beta is greater than 0, and we consider the following problem. So the alpha u is equal to lambda u. Here we take lambda equal to p to the power beta n, because the p-adic norm can only take values p to the power of some integer. So we can apply the Fourier transform to both sides of this equation 13, and we will obtain the following equation 14. As you can see, we have this difference in the first brackets, and it will be only equal to 0 if the following condition holds. So beta is equal to k alpha for some natural number k. So from now on, we will suppose that this condition 15 holds. So we have the following proposition. If this condition for alpha and beta holds, then the equation has the set of solutions in Lizorkin space phi that has the following form for all n integers. And the next proposition is for distributions. So if a radial eigenfunction is a distribution and it satisfies this equation, then it also has this form 16 from the previous proposition. So next step is considering the equations for functions of two variables. So we have u of t and x, and this particular equation was considered in a paper by Anatoly Kochubey, and here t plays the role of time, and this equation in some sense is an analog of the wave equation for classical case. So we call the function f of variables t and x the non-Archimedean plane wave if it has the following form. And it was proved by Kochubey that for any alpha greater than 0, this non-Archimedean plane wave satisfies this equation 17. So in my work, I considered the Cauchy problem for a similar equation, but here we do not have the power alpha on both sides of this equation. We have the operator d alpha with respect to t and d beta with respect to x. So the goal was to look how these parameters alpha and beta should be connected and to find the solution of this equation. So the following theorem was proved. If alpha is less than 1, beta is greater than 0, such that beta is equal to k alpha for some k. And we suppose that the function u0 from the initial condition of the Cauchy problem is an Lizorkin space. Then this problem has a solution u, which is a radial function in t, which means it only depends on norm of t. It belongs to Lizorkin space for each x with respect to t, and for each t with respect to x. So we can find the representation of the solution. For this, we take the Fourier transform with respect to x on both sides of our equation, and we obtain the following equation. We suppose that the function v is the solution of this equation. Then if we take the inverse Fourier transform, the function u would be a solution of the initial equation in the Cauchy problem. So we will be looking for the solution of this equation 21. We introduce some notations and rewrite this equation in this form 22. And we can see that this problem is a radial eigenfunction problem for the operator d alpha. So now we can solve this, applying Fourier transform, now not with respect to x, but with respect to t. So by the previous proposition, we do some calculations. And we obtain that our equation has the following solution, 23. And the solution belongs to Zorkin space. Here we introduce the function b. It is represented on the spheres in the following form. So we also consider this problem for generalized functions or distributions. Here we denote phi prime of QP plus phi prime of QPN as a set of all distributions, which acts on the space of test functions phi and has values in the space of distributions phi prime. So we have the following theorem. If the function f is in this space, is the generalized solution of our equation, that is the following relation holds. And if f is a radial function with respect to t, then f belongs to the space of test functions. And in addition, if f of 0x is equal to 0, then if of f of t x is equal to 0 for all t. We also have the following lemma. So if beta is equal to 0, is greater than 0, sorry, and u is a bounded locally constant function on QP, then the distribution d by the n of u coincides with this integral representation. So it follows from this lemma and the previous theorem that all locally bounded constant solutions of this equation are also generalized solution of the class considered in the previous theorem. Therefore, all the solutions that we found in the previous theorem are unique in the class of functions radial in T and bounded locally constant. We also found the estimate of the solution, so we suppose that all the previous conditions of our theorem holds, and then the solution of the problem satisfies the following estimate in L1. So we can bound it by the norm of L1 of U0, where U0 is the initial condition, multiplied by some constant p to the power 2n gamma. Gamma is some positive constant greater than 2 over k. Here you can see the main sources. And that's all. Thank you for the attention.
Thank you, Mariia, for informative presentation.